off, on and off, on and off. No. In reality, if I do this very fast, what happens? The effective current is lower. So, if this is, like, say this is 1 amp, then the red one will effectively run at 0.5. But I'm not, because to take 1 amp and control it to 0.5 is complex. So instead, it's much easier to do this. Just on, off, on, off, on, off, right? But I can also do off, on, off, on. And I can do 20% PWM. And so this is how we control our motor. Now, this is for a different application using the same tools.
Well, we can do that for this too. What we do is to use a controller to rapidly open and close the switches multiple times per cycle in a pulsating pattern, each pulse varying in width. This is known as pulse width modulation. The cycle is broken up into multiple smaller segments. Each segment has a total amount of current that could flow.
So make a guess. If we do this, what's going to happen to the current? Look at the width of the pulse. It's not constant like this. It's also not constant like this. We play with it. So what's going to happen if I send that kind of pulse?
Brightness of the bulb. The brightness of the bulb.
To the current, not the bulb. Remember, if I half this into 50%, the effective current is 0.5. If I make it 20%, then the effective current is like 0.2, right? So, if I start off with a narrow pulse, and then kind of make it bigger here, and then make it smaller again, what do I see?
Second wave.
Exactly, right?
Yeah.
So that's how you make the sinusoidal shape and how you gradually increase it to the peak. This is how you convert from a square wave to a sine wave.
By rapidly pulsating the switches, we control the amount of flow occurring per segment. This will result in an average current per segment, which we see increases and decreases, thus giving us a wave. The load will therefore experience a sine wave. The more segments we have, then the closer it mimics a smooth wave. We can control the output voltage by controlling how long.
Okay? So, that's what I want to show with that. Okay, let's take a quick break and then we'll talk about hybrid systems and do a little bit of an in-class exercise.
current system directly connects.
start again. Let's talk about hybrids. Now, there are many different types, but when it comes down to hybrids, the question is, the bottom line of the question is, how do we want to join the two powers, or the two sources of power, right? Between gasoline and electric. And you do have to remember that gasoline engines need transmissions. To add to the complexity, then, if you operate on gasoline engines only, you need transmissions. You need the different shifting because of the power band, the narrow power band. The gasoline engines is also more efficient in high speed. So we need to decide now, how do we want to merge these two sources of power, right? So you got the ICE engine and you have the electric motors. Now, we can, it comes down to two different major types, right? This is called a parallel hybrid, because they basically work together. Another philosophy which Nissan uses is basically you charge your battery, and then your battery runs your electric motor. Okay? So here your battery, and here we're just talking about excitation, we haven't talked about regenerative. But there is parallel systems and then there is series systems. And in series hybrid, you actually never, the ICE, the combustion engine, never actually touch the wheel, right? So this is wheels. So in a series, purely series hybrid, like Nissan e-Power, you actually never see your combustion engine directly connected to the wheels at all. In parallel systems, you do have connections. But then, within the parallel systems, you also have the question of how are they going to work together? Are they going to work together at the same time? Or are we going to switch between one or the other? Or maybe both, switching and also together. So this opens up a whole different way of approaching the same problem, right? But the problem we are faced with is that we are merging between internal combustion system and electric. And this needs transmission. This is also high efficiency at high speed. Narrow power band. Also narrow window of efficiency. Here in the electric, you don't need no transmission. It can span all speed. It is more powerful in low speed, more efficient in low speed, and more powerful too. Good response in low speed. Wide power band and wide efficiency, relatively speaking, but better at low speed. because of the stop and go driving. So we're going to have to come up with a system that kind of take the strength of each, right? Toyota, I think, developed a very innovative hybrid system, which, you know, you are always debating whether you want experience or do you want efficiency, because sometimes you have to choose. But let's take a look at the Toyota one first, because I think, well, first of all, they are one of the first. So it's very, very innovative. It's called the
Familiar with the
ECVT.
CVT transmission. It uses a simple belt and pulley system that gives you infinite gear ratios and offers a smooth, seamless power delivery. But do you know about the ECVT? Hearing the name, you might think it is a normal CVT where just a little electronics have been added. But the reality is quite different. Unlike a normal CVT, this has neither pulleys. The ECVT isn't even a transmission. It's actually a power split device. This is the technology that helps hybrid cars achieve those magical mileage figures. So in this video, we will dive into the details of the ECVT to understand what it is and how it works.
Okay, so at the heart of the Toyota Hybrid Synergy Drive, are you familiar with the Toyota Hybrid? Yeah. So it's really a power split device, okay? They are always connected at all time mechanically. So there is no clutch detaching or attaching itself. And the motor actually does the job of the ratio changing too. This is what I think is very innovative.
The first question in your mind is probably, if there are no belts and pulleys, then how does it work? See, CVT stands for Continuously Variable Transmission. That means smooth power delivery without any interruptions or jerks. Now, whether this delivery comes from belts and pulleys or from gears doesn't make a difference. The only difference is that instead of belts and pulleys, the ECVT uses a planetary gear set. It's called planetary because it looks like our solar system.
Of course you know this, right?
It actually works to divide the power. That is why the ECVT is technically called a power split device. Now here, it's not just the engine and wheels involved. There are also two electric motors. They are named MG1, meaning motor generator 1, and MG2, meaning motor generator 2, which is also known as the traction motor. Now understanding the role of these two is crucial. First, let's talk about the traction motor.
So, two motors, two different functions. MG1 is mainly responsible for generation and changing of the gear ratio for the gasoline engine. MG2 is strictly traction, like give you the torque.
This is the motor that directly spins the wheels. When you drive an ECVT car from a complete standstill, often only the traction motor is working. At that time, the engine might remain off. That's why a hybrid car starts so smoothly and silently. Apart from this, it also handles regenerative braking. When you take your foot off the accelerator or apply the brakes, this motor becomes a generator. Basically, the energy that normal cars waste as heat, the ECVT captures and stores.
Okay, so MG2 is mainly traction and regenerative braking. But generating electricity using the gasoline engine is on MG1.
As regenerative braking, this motor also acts as a power assist in high load situations like heavy acceleration or steep climbing. This motor supplies power to the wheels to assist the engine. On top of all this, the traction motor does one more job, moving the car in reverse direction. Polarity is switched,
Okay.
called the generator motor.
So now let's talk about MG1.
Its job is a bit different from the traction motor. It acts like a starter motor to crank the engine. That is why ECVT cars don't have a separate starter motor. And when the engine is running, this motor acts as a generator to produce electricity. This electricity either charges the battery or is supplied directly to the traction motor to provide extra torque.
So the source of charging are two. One is from regenerative braking, but also from the gasoline engine. So even if you're not braking, you're also charging the battery.
But the most important job of this motor is controlling the engine RPM. And this is where the ECVT magic begins. As we discussed, the ECVT has three main components: the engine, motor generator 1, and motor generator 2. In the planetary gear set, these three components are interconnected. If you change the speed of one, it affects the others. Motor generator 1 is connected to the sun gear, shown here in green. The engine is connected to the planet carrier, the red gears.
Okay, you do remember in our discussion about planetary gears, and especially its application in the automatic transmission, you can actually change the ratio by turning some of the other gears. So, for example, this is the sun. Well, this is the sun, the ring, the planets, and the ring, right? Let's say your sun, the planet is connected with a planet carrier, right? Let's say the sun is your input, and the ring carrier, the planet carrier, is your output. If your ring is stationary, you have a certain ratio. But if your omega r is something, it's not zero, the ring rotates, the sun rotates, the carrier rotates, the planet carrier rotates. The ratio between the sun and the planet carrier changes if you rotate the ring. And that happens to all other combinations. Okay? So you can lock one and just get a certain ratio, but you can actually play with the ratio by rotating the ring. In this case, we are doing it a bit different. What was it? MG1 is connected to the sun, and the engine is connected to the planet carrier, the red one, but the wheel is connected to the blue one. And so the input and output is actually the engine. The red is the input, the blue is the output. But by manipulating the green, you can manipulate the ratio. Okay, that's the core idea.
And motor generator 2, or the traction motor, connects to the ring gear in blue.
So MG2 can help anytime it wants to on the ring. But forget about that ring for now. Forget about MG2 for now. This is about the gasoline engine and manipulating the ratio.
And the drive wheels are also connected to the same gear. So first, when you start moving the car from a standstill, there's no need to start the engine. The traction motor alone draws power from the battery to move the car. As speed increases, the traction motor isn't enough. That's when the generator motor enters, instantly spinning the engine to start it. Now both the engine and traction motor work together to turn the wheels. Simultaneously, MG1, the green motor, rotates, acting as a generator to charge the battery. When you stop the car, engine power isn't needed, so it shuts off immediately. However, as the wheels slow down, they spin the traction motor, which recharges the battery through regenerative braking. Now, if you need to reverse the car, there is no reverse gear. The traction motor simply rotates in the opposite direction, and the wheels also start rotating in reverse. But the true meaning of CVT is infinite gear ratios. A traditional CVT has belts and pulleys. By increasing and decreasing the pulley size, we get infinite gear ratios. But an eCVT has fixed gears. So how do we get infinite gear ratios?
Okay, so this is where we're going to change the ratios.
The secret lies in the speed of motor generator 1. If the green motor spins faster than the engine, less engine power reaches the wheels. The wheels turn slowly but with high torque.
Okay, so this is the first condition. The first condition
Engine power reaches the wheel.
is when the engine just, so you keep the engine rotating at its narrow efficiency power band. And what speed you want is manipulated by the green motor. If you rotate this fast, then you are simulating like a first gear or second gear.
The wheels turn slowly but with high torque. This acts like your low gear, like first or second. As you reduce the speed of the green motor and bring it to a stop, the wheel speed increases. And this acts as your mid gear, like fourth gear.
Okay, so if your green motor stops, like equals 0, you lock it in, but this one is the sun, by the way. Then you have like a third or fourth gear.
And when you spin the green motor in reverse direction, wheel speed increases further. The faster the motor spins in reverse, the faster the wheels will turn, acting as your top gear.
So for your top gear, you actually reverse the green motor, and you'll get even higher ratio.
So, by simply setting the motor speed to any RPM you want, you can achieve any variable gear ratio you want. In an eCVT, the motor speed and polarity are controlled by an electronic system, which is why it's called an eCVT. In an eCVT, the computer uses the motor to keep the engine in its best efficiency zone at all times. The engine doesn't care if the car is doing 10 speed or 50 speed. It runs in that sweet spot where fuel use is lowest. The traction motor handles the rest. Also, in traffic, the engine stays off as long as the battery has charge. This reduces fuel wastage. Simply put, the eCVT doesn't let the engine waste fuel. It runs the engine only when necessary and uses motors the rest of the time. This coordination gives you those high mileage figures. An interesting fact about the eCVT is that it doesn't use a normal Otto cycle engine. It uses an Atkinson cycle engine. But we'll discuss that in another video.
So an Atkinson cycle is basically a more efficient Otto cycle. It is very sluggish though. That's why you're not using it independently. You use it in combination. So that's a perfect engine for a hybrid because you got a sluggish but very efficient gasoline engine, but then you got the motor to give you the torque. So that is the Toyota one. Now before we discuss the Honda version, how would you want to control, and I have this quick exercise here, okay? So let's get to a discussion. So you have this scenario, right? You got the urban congestion, scenario A, frequent stops, 0 to 30 kilometers per hour. And then you have segment B, you have climbing at 60 kilometers per hour. You got segment C, which is steady. And then you got segment D, which is a 5% grade descent. So how would you control what you want to use? How you want to combine them together? If you can control all of them. When do you want to do what? Okay? So what I want you to do now is I want you to maybe think about it and have a few ideas on your own. Okay? And then after that, I want you to do a study buddy with the AI. Like choose Gemini. Do you use Gemini or ChatGPT? Okay? So do a little bit back and forth, asking the AI to teach you how to think about deciding on these factors. Okay, go ahead. So first generate your ideas, and then you talk to the AI later. Okay, so you generate your ideas and then check with AI. But in your prompt with AI, I want you to prompt it to do a teaching you how to think, not just giving the answer. Okay. Okay? So, what do you find for each of these scenarios?
Yeah, for second A, which is urban budget congestion 0 to 50 per hour and stops. I mean, it's quite, like you said, it's more efficient to use electric power instead of IC because the peak efficiency there in IC and efficiency is basically at 2,500 RPM
Okay.
and 75% load. So,
But what happens if your state of charge is already low at one point?
Therefore, there's a regenerative decision, which there it is like full, I would say fully regenerative mode, which by braking, frequent braking and frequent stops, it also helps with regenerating the electric zone.
Okay. But because regenerative braking is not as efficient in very low speed, as in like traffic jam speed, right? So you will still run out of battery charge. So you still have the logic of turning on the engine if it gets to 20%, right?
Yes.
Okay. What about segment B?
Well, segment B, it basically, well, it's climbing. Of course, it needs first high torque and high acceleration. Therefore,
Well, not acceleration, but you need torque to overcome. Yeah.
so basically we are required for high torques. Therefore, it requires both ICE and power, also supported by the electric power, the electric motor.
Okay.
Therefore, the motor will give extra torque. But when we are saying like relying on the battery itself, like alone, it will decrease, like it will eat up all the state of charge.
Yeah.
And therefore, the most efficient and the most better way to do it is by combining the ICE
Yeah.
with supported by the motor.
Iman, you wanna add anything to the discussion so far?
For the climbing part, the electric motor only needs to kick in to decrease the RPM of the motor to keep it in its
Sweet spot.
efficient
Yeah.
running
Uh-huh.
pace. And for the cruising, for the urban, depends on the state of charge. Most of the time, depending on the power consumption and the battery size, you're gonna use the engine to fill up the battery,
Right.
and then you're gonna go electric mode and like lead forward. As soon as the state of charge drops to a certain point, the engine kicks in back
Yeah.
again and then charge the battery. But most of the time, it should be the electric motor more rather than the engine.
Right. Okay, Mika, you wanna kick off segment C? Oops.
C is highway.
Yeah.
I think highway is highway says that if like the ICE is more efficient, like in high speed, right? But so if the ICE is very efficient enough for like driving and cruising, so the electric motor just doesn't like power the wheels, so it's already efficient enough car, sometimes when the IC is already running at the efficient state, sometimes it will charge the battery
Yeah.
also.
Yeah. Now, it does, when it charges the battery is yet another logic, right? So you have, what is also possible is doing a predictive charging, because if the GPS can tell you that there is an upcoming downhill, which is segment B, for example, what you want to do is you want to preserve a certain amount of room for the charging, because then you cannot take advantage of the going downhill, for example, right? Okay, so that's kind of a more advanced predictive charging and regenerative charging. Want to add anything, Ivan, on segment B or segment C?
Well, segment C, just like the logic for segment A and C, segment A is mostly like 10% engine and then 90% EV. But then for segment C, it's more towards 75% engine and then 25% EV. Because the thing is, it's a little bit unrealistic to like cruising 75% constant load.
Yeah.
So at a certain point, the excess load, the excess energy that the engine is providing will be charging the battery. So when the battery is like up to 80%, which is the sweet spot for the battery, the excess energy cannot be stored more. So you use it to with the in combination with the engine also to, so it's more like 75, 25 logic like that.
Yeah, so it's kind of, think about it, the engine must run at the efficiency window, and therefore at that point sometimes the demand for the engine is not high enough to get it into the efficiency window. So you actually want to charge your battery so it puts more load. So sometimes you do want to load the engine a bit more, because if the load is too small, then you cannot be that efficient. So there is this is a very dynamic decision making factor, right? But I think Toyota has perfected that so much. I have other YouTube videos on Hondas and also Nissan in that PowerPoint. I uploaded the PowerPoint in Google Classroom.